So our next speaker is Pietro Speziali from University of Campinas, and he's going to talk about large automorphisms of prime order of algebraic curves in positive characteristics. So Pietro, please.
Thank you very much, Mateus. I will have to talk in English, if allowed. And first I would like to thank the organizers for this wonderful event in honor of our dear friend Fernando, and Juan for his wonderful, very touching presentation about Fernando. Before going into the talk, I would like to say some words about him, because Fernando was, before I met him, was my scientific hero. Like half of my PhD or half of my master's thesis or dissertation was with his article. And then I met him, and he became one of the greatest friends I had in life. So recently I've been told that the characteristic of the unforgettable teacher, the unforgettable professor, is someone who is a real person, who shows affection, who impacts your life with his charisma, for being a nice person and a great friend. And this was Fernando for me and for all of us. And I wouldn't be here today if I hadn't met him as a professor of Unicamp. Unfortunately, for some months, we never had the chance to be colleagues. Yeah, this was a great honor for me. So, yeah, I just wanted to say this. Also, I chose this topic today because it was the last talk I presented to Fernando in the last workshop on finance fields first in Erlandia, and also because the story of this talk, this work is a little bit more complicated than that. But the first thing that prompted me to study these automorphisms was a question that someone made me after a canonical juice at Fernando, one of Fernando's seminars. So just to see how much impacted our lives, even if not in our research, even when not directly. So let's go in the talk. So what is our motivation? I start as a motivating quote, it's something I like to do. I took this sentence from the beginning of chapter 11 of the book, Algebraic Curves of Finite Fields by Professor Hirschfeld, Professor Corpos, and Fernando. Basically, why are we interested in curves with many symmetries or many automorphisms? Because usually they carry through a legacy of beautiful geometry, so they have very nice properties, and they're also good for applications. As we will see, one of the main examples of this is everyone's favorite Hermitian curve, which will feature in this talk of us. So our first example to see also the challenges that the positive characteristic pose to us is the so-called quantum work. As you all know, any curves of genus 3 which is not hyperelliptic, is isomorphic to a plane quartic. So here you see this very nice equation of the plane quartic, x to the cube plus x, y to the cube plus y equals 0. Over C, this is one of the examples of a curve that takes the Hurwitz bound 84 to -1. So it has an automorphism isomorphic PSL27 or PSL32. And what's the size? 168, which is, as I told you, 84 to 21, which is Hurwitz bound. But what happens is that over an algebraically closed field of characteristic 3, this curve is isomorphic to the Fermat curve, x to the Fermat quartic, x to the 4th plus y to the 4th plus 1 0, which in turn is the Hermitian curve. And here you see how. Sorry.
Pietro, excuse me, just a moment. Can you please talk a little closer to your computer, because maybe the microphone is positioning and we cannot hear very well when you go far away from your cam.
Is it better now?
It's perfect. Now it's perfect.
So, okay, thank you very much. Sorry for that. Sorry about that. So, I mean, the main point here, the take-home message of this slide, just to resume, is that in positive characteristic, you may have a lot of automorphisms. I mean, here we are, it's a function, I mean, if you see PSU33, here size with the automorphism group of the Klein quartic in a Fourier field of characteristic 3 has size 6048, which is bigger than 16 g to the fourth. So Hurwitz characteristic 0, you have the Hurwitz bound. So the automorphism group, the size of the automorphism group is a function which is at most linear in the automorphism. While in positive characteristic, it can be a polynomial of degree 4 up to 4 in the size in the genus of the curve. So let's establish some notation, some common ground. We will work, I know this is finite fields, but for automorphism groups, the natural setting is to study where algebraically closed field of characteristic. Well, in this case, we will have also feature characteristic p equals 0, but the most interesting cases will be fields of positive characteristic. X is a projecting, singular, and absolutely reducible curve over K, but usually we will use some singular models, possibly plane models, because they're actually easier to deal with. So we will have the function field of X, K of X. What's an automorphism of a curve? So the shortest way to see this is that, okay, when you have a curve, you have the field of rational function associated with that, which is K of X. And well, for a field, it's easy to see that you have automorphisms. And this is the automorphism group of the curve. And this also shows like immediately that since curves that are birationally equivalent have the same function field, that the automorphism group is an birational invariant of curves. And also the genus of X will always be denoted by G. So basically what we will need, what we will see here is some relationship between the primes divide the order, the primes dividing the order of the automorphism group, the genus, and some consequences of that. So some effects which are well known, some classical effects regarding automorphism groups. When you have the genus is a non-negative integer, so it can be when it's 0 or 1, what are the possibilities? Genus 0, you always have basically a rational curve. So basically they're all birational equivalent to P1, to the projected line. So the automorphism group is PGL to K. When the genus is 1, you have elliptic curves. And in this case, also in this case, the group is infinite, because for the group law, from the group law, additional law between points of elliptic curve, it's easy to have an idea that the curve itself somehow embeds into its automorphism group. So it's infinite. But whenever you go from when the genus grows from 2 onwards, then it is a finite group. So you may use the power of the powerful tools of finite group theory to study that. For hyperelliptic curve, for instance, the structure is known, and this is why usually I will discard the hyperelliptic case in this talk. There is also the inverse Galois problem for curves. So basically, that's that any group can be realized as the automorphism group of some curves. Actually, have infinitely many curves which are not isomorphic with a unmeeting group. But an interesting fact that is a beautiful result by Pietro Speziali, we will be using in our talk, is that this is not true when the genus is even. When the genus is even, the structure is more rigid. So you have actually a lot less, you can control the possibilities. And this is will be interesting. This is interesting when you want to determine the structure of the automorphism group of a coordinated genus, which will be the case. So what are we talking about now? Basically, we give this definition. If you take a prime number Q and take a curve defined over a field K is a Q curve whenever the automorphism group of X contains a cyclic group CQ of order Q. So why do we call it tame or wild? Tame when P equals 0 or Q is not a characteristic on the right field, because in this case you have if you have ramification, you have tame ramification. In the other case, you have wild ramification. So this is why we gave this definition, which is non-standard. Homma in 1980 established this is the analog of the result of the order of the size of primes dividing the automorphism group of a Riemann surface, which it was well known. So basically, what happens here? Let Q be a prime, which is the order of an automorphism group of a curve. Either it's equal to 2g plus 1, or it's smaller than or equal to g plus 1. So you see, what we'll be interested is in classifying the cases where this or the order of this automorphism is big with respect to the genus. So in particular, we will be dealing with G plus 2G plus 1 and G plus 1. So the first result in the very same paper in 1980, Homa also characterized the curves, the 2G plus 1 curves, the wild and the tame 2G plus 1 curves. So basically what we are saying here is that when you have a prime of order 2G plus 1 in the automorphism group of the curve, what do I mean by classifying? We are giving a plane model. A plane model in this case is giving like the relationship between the two generators of the function field. So this is a classification up to birational equivalence. So basically a group of order 2G plus 1, when it is a prime, fixes a rational subfield. So the quotient curve is P1. And also when you think geometrically this action on the points of the curve, it fixes 3 points, which gives you the equation in the item A. Now, when it's wild, so when the characteristic is 2G plus 1, you cannot use Kummer theory as in the former case, so you have to use Artin-Schreier theory. And in this case, basically what this equation tells you is that we are always fixing a rational subfield. So the quotient curve is isomorphic to P1, but then we are fixing just 1 point. This is because this is due to the wide ramification. So the first result we had in this joint work with Nazar is the classification of the G plus 1 curves, which is the next result. So basically, as you can see, the situation is similar, but yet more complicated. In the tame case, basically, what happens? A prime of order G plus 1, if you have a prime of order G plus 1, which is the order of automorphism, then, okay, plane model, why do we get to this plane model? Because this automorphism fixes 4 points this time, and the fixed field will always be rational. So this gives you that equation, which is X capricciado RSTA. In the wild case, the situation is more complicated, slightly more complicated. You always have hyperelliptic curves. So in one case, you have 2 fixed points, or if you can have just 1. And this accounts for the 2 kinds of equation, Y capricciado ABC or Z capricciado DEL. This is basically what happens. So in these 2 cases, we have the full classification. So it's interesting to think, okay, I have these curves classified just by the order of automorphism. What can I say more? Can I have the full automorphism group of this curve? Because if you think the Klein quartic I presented you, mean that in characteristic 3, it has a huge automorphism. So can this be the case? But before doing that, it's also fine. It's also interesting to say, okay, can I classify which curves are hyperelliptic among the G plus 1 curves? Because for the 2G plus 1 curves, Hom already did that. Well, you can. Actually, basically, the take-home message here is that you take the plane equation and then you impose that you have a central evolution, which must act on the fixed point by the group of order G plus 1. And this gives you some restrictions on R, S, and T, so on the exponents. Actually, 2 have to be equal, and when you have 1, the second one is completely determined as G plus 1 minus that guy. So now into full automorphism groups. What we managed to prove is that whenever you have a tame 2G plus 1 curve of genus bigger than 3, then the group of order G of order 2G plus 1 is normal in the automorphism group of X. This means that the automorphism group is small. Actually, it's at most 3 2G plus 1 or 2G plus 1. In that case, the curve is hyperelliptic. Unless this curve is isomorphic to the Hermitian curve. And this may happen, actually. I mean, there are a lot of instances when this may happen. I will not get into the detail, but I want to tell you that in this case, the technique we used was rather surprising. Because the first thing we proved is that, okay, from a result by Seyama in 1982, we knew what happened in characteristic 0. And this always happened when the group was small, the size of the group was smaller than or equal to 84G minus 1. So the question was, what happens when it's bigger? Well, if it's bigger of the whole orbit bounded for G minus 1, then we managed to prove that the automorphism group had to be a non-abelian finite simple group. This was rather surprising for me, and then we also stumbled upon this very nice result by Dobin, which is purely regarding the non-abelian finite simple groups. So basically, what we say here, if you have an abelian subgroup, that cannot be too big. When the group is not PSL to Q, because you see, if you have the size of an abelian group to the cube, is smaller than the size of G. So you see, here we have a cyclic group of order 2G plus 1, in particular is abelian. So, and the automorphism group must be an abelian finite simple group. So basically, I would be done if I know what happens when the automorphism group of a curve is bigger than 8G to the cube. But luckily enough, this is a very classical result by hand. This is actually what's his PhD thesis, which tells you, okay, take a curve that has more than 8G to the cube automorphisms. Then you have just 4 infinite families. These are all the possibilities you may have for the size of the automorphism group. So in 2 cases, you have an hyperelliptic curve. It's also interesting to mention that in the first case, when in the second case, y square minus x to the p to the h minus x, then you recover y square minus x to the p minus x. In that case, you have the curve discovered, the hand considered. So in that case, it's also a 2G plus 1 curve. But it's hyperelliptic, so we're not considering this case. Or you have the remission curve. And we had examples, because if you remember the Klein quartic, it is isomorphic to the remission curve over F3, over F9. And in that case, you have 7 2G plus 1, which is a prime, which is an ordinal automorphism. Actually, there are a lot more cases when it happens. So we know that in this case, this may happen. The case which was still standing was the case of basically the Suzuki curve, which is the last one, the DLS curve, the case 4. In this case, actually, it was easier to discard this case because, funnily enough, the Suzuki group is, of course, it's a famous family. Supergroups are famous, form a famous family of non-abelian finite simple groups. But, well, what happens? His order is not divided by 3. And what we managed to prove, this is a technical level, it's in this presentation, that whenever you have a 2G plus 1 curve, such that the size of the automorphism group is equal to 4G minus 1, then you need to have an automorphism order 3. A guy of order 3 actually normalizing the guy of order G plus 1. So this is a very short resume of what we managed to do for 2G plus 1 curves. So next we go to the automorphism groups of G plus 1 curves. Now here we have the problem, not the problem, we have the technicality that the characteristic of the underlying field cannot be neither 2 nor 3. So we take a non-hyperelliptic attaining a hyperelliptic G plus 1 curve because, well, for hyperelliptic case, we know what happens. In this case, the situation is somewhat similar. You have because you have that for the smallest genus we consider, which is 4, you have an exception to the normality of the group of order G plus 1, which is Green's curve, which automorphisms are isomorphic to S5. But then in the other cases, you have the CG plus 1 is normal in the automorphism group. So actually, the automorphism cannot be big. Because in this case, we have 4 fixed points, which means that actually any guy normalizing the automorphism group of order G plus 1 must be isomorphic to a subgroup of S4. But actually, at most, you have guys who order 4 inside. So that's pretty much the end of the story. What happens here is that how we managed to prove that. And these were the fact that you may notice G plus 1 is a prime, so G is even. So this is a curve of even G's. These curves have even G's. And so we used this wonderful result by Massimo and Professor Massimo Giuletti and Gabriel Kochmarush, which tells you, okay, if you take any field of characteristic which is not 2 and a curve of even genes, then these are the possibilities. for the automorphism group of this curve. You have curves of the automorphism group may have odd order, or you have always these ODG is the Brouwer curve or odd curve, which is the maximal normal subgroup of odd order, which the maximality is respecting. So you see a lot of nice groups here. I mean, you have LZ, you have some sporadic groups, you have PSL or P gamma L2Q, PSU 3Q, etc. So the fact that we had a finite list of possibilities allowed us to compute actually with quite efficiently the cases and discard the cases which were not possible. Of course, this involved a lot of consideration of the structure, some rules and computations. So for the wild 2G, what happens for the case of the wild G curves? This case is interesting. So we discarded again hyperelliptic case. So we get, if you remember the slide, we got all just the last equation. And in this case, the group you have, these are curves given by separated polynomials, meaning that you have, and these are always arbitrary curves actually. So you have an equation in Y, which is a separable polynomial of 3G plus 1, and a polynomial which is at most a cubic polynomial in X. So the techniques here were different, but I want to tell you, what I want to stress that in some cases you may have curves of with a huge automorphism group, because in the case of the curve C, you can see on the slide, we have something which is of the order of 3G to the cube. So we are really close to the classification of 10. Actually, I believe it will be of interest to try and classify all the curves with at most G to the cube automorphisms, but it seems a rather difficult task. So this could be another interesting thing to start to think about. So I want to end this with some questions or some further direction of this research, which I hope to present in the next installment of workshop of finite fields maybe. And some of these questions are more related to finite fields. So of course you may ask also, can we classify G and G minus 1 curves? So that's prime, it can be equal to the genus or G minus 1. Actually, we have some partial results in there. And of course, you may determine the full automorphism groups. Then you may ask, what's the Jacobian of these curves? Can I decompose it? And this is related to counting points of these curves actually. And so you may ask when these curves are ordinary, so when the P rank, whatever the P rank is equal to the genus, or super singular, the opposite case, when the P rank is 0. And you may also ask, well, is there any case when these curves may have many points? Of course, you have the remission curve in these families for the 2G plus 1 curves, so you have hope that this happens. This is something I'm really interested to study, or not. Maybe you can just comment. So I guess my time is running out. Correct me if not, Matheus.
2 minutes, Pietro.
Okay, so yeah, I went fast, but yeah, basically this is all I wanted to tell you. I want just let me end with one of Fernando's favorite sentences whenever we say hi, we say bye to him. He always said, "Estamos en contacto." And so this is a picture we took in my first month in Campinas, and that's that agasalho of Unicamp might seem foreshadowing somehow. We went to Valinhos, I guess. So yeah, it just seemed fit to end this talk with a photo of our great friend. So well, thank you all.